Now we have defined what are Lorentz transformations essentially, but and then that they form a group. Now the way we define this particular thing is very interesting in the sense that we say that any Lorentz transformation should uh, should leave the metric invariant. Now this is an extremely interesting and interesting scenario because the Lorentz transform it leads to certain very interesting features essentially. Let's look at some basic features of the Lorentz group. Now uh, Lorentz group has much more interesting structure than just Lorentz transformations. The reason why this becomes interesting is because the Lorentz group has much more interesting structure than Lorentz transformations itself, because which you would not uh, sort of phantom in the case of without okay we just studying the way we are doing earlier ways essentially, like what we did was, okay, let me just write down in terms of say gamma and beta gamma and so on. So okay, if you do it that in that particular fashion, we may not understand completely the properties of Lorentz transformations essentially. So the this group what it leaves invariant is this particular thing. Now this gives you some very interesting features essentially. So let's look at some of the features of the Lorentz group essentially, and then we'll start looking at generators and stuff like that essentially. So some features of Lorentz group essentially. Now what we will have, what does the Lorentz transformation contain? What does the Lorentz transformation? So typically we will think in terms of 3 boost essentially, it will contain 3 boost, but the group also contains rotations essentially. We will see that in greater detail as we go along, because so what we will see is that normally when we say Lorentz transformations, we are really focused upon boost essentially. We are saying that there are this beta gamma and everything, but it leaves within the space part, there could also be other rotations essentially. So the Lorentz group is much richer. Okay, the Lorentz group is much richer. So Lorentz group is equal to boost anyway. There are 3 kinds of boost essentially. So what we will see is boost, I mean x and t transformations. So these are 3 because x0, x1, x0, x2, which are obvious essentially, x0, x3. But then there could be also, because it forms a group, there could also be rotations within this side essentially. So you can think that you can have a Lorentz group in such a way that you can have 1 0 0 0 0 0 0, okay, the Lorentz element, and here you can have a O3 group essentially, a rotation group essentially completely, which leaves the vector x1 x2 x3 invariant, which leaves that is the power of the group. Okay, so you can think that you have independence, you don't have anything, but here you can have rotations. So rotation group between the 3 space directions. Okay, but Lorentz group doesn't stop here. That's the thing, that it is such a rich structure essentially, which is very nice and very interesting in that direction. So you have boost, which are 3. Okay, there are rotations, but then there are 2 discrete, not continuous, 2 discrete transformations which also leave my condition, which also leave the this condition invariant, lambda transpose lambda is equal to G. So this condition is the sacred condition. Essentially, this is your sacred condition. This condition is left invariant with two more discrete things. One is called P, another is called T. So I'll tell you what P and T are, and then we'll come back to boost and rotations and all the generators of Lorentz group and so on. So essentially, okay, these are important. So what are P? P is space inversion. We'll come back to it again and again when we'll do the Dirac equation essentially. So the P is defined in that x goes to space part, x goes to minus x. So this P has a matrix representation 1 0 0 0 0 minus 1 0 0 0 0 minus 1 0, so 0 0 0 minus 1. Okay. What does P do? P acting on x will take it to minus x essentially. P acting on x will take it to minus x. It is nothing but space inversion. Now this is not x mu, okay, this is only x bar. Okay. So P will leave x0 is equal to x0. P on x0 is equal to x0. Okay. P on x0 will leave x0. P on x bar will leave minus x bar essentially. So this is space only inversion. Okay, this is space inversion. We'll come back to it later on. We'll call it something else essentially, but we'll come back to it as something. Now, what does space inversion also do? It also satisfies the condition that P transpose G P is equal to G. It also leaves the metric invariant under this condition. So it forms a part of the Lorentz transformations. It also forms a transform part of the Lorentz, but not continuous Lorentz transformation, but discrete part. So it has two Lorentz transformation. So Lorentz group has two continuous rotations, or one is boost, then one is rotations, which are continuous transformations, and two discrete transformations associated with it. Well, the first discrete transformation, this is discrete. I keep repeating this. This is important. This is discrete. This is discrete, so it means that it is not like a continuous part essentially. Okay, this is discrete. This is called space inversion. The second discrete part is called time inversion. So T changes x0 to minus x0. T leaves x bar. So this has a matrix representation minus 1 0 0 0 0. Of course, it satisfies the condition T transpose G T is equal to G. Satisfies the condition T transpose T. So this is called time inversion. So these two discrete symmetries are a part of the Lorentz transformations. These are important, and remember them. We'll come back to them later on essentially when we are dealing with the solutions of the Dirac equation and the discrete symmetries associated with it essentially. Okay, good. So to summarize essentially, what we are looking at is Lorentz transformations have transformations R is equal to boost plus rotations plus P plus T. This is the full ambit of Lorentz transformations. Okay, this is the full ambit of Lorentz transformations. Now we should later on, as we will see, actually there are some important reasons why we need to classify the Lorentz transformations essentially. So there is some as we will see there are very important theorems in quantum field theories and also relativistic quantum mechanics and everything essentially, which has to do which have extremely important theorems. They require a particular classification. These discrete symmetries play a very important role essentially. They play a very important role, and they have a very uh, important feature of Lorentz. You have to classify the Lorentz transformations. There are they only satisfy there are only a particular class of Lorentz transformations which are extremely important essentially. So what are this classification of Lorentz transformations essentially? I'll come back to what is important to that. I may use some technical words, but we will see essentially. So what we have seen is we'll start with the same condition, G mu nu is equal to lambda. Okay, let me just use the same notation as above. Uh, this should be rho. Now taking determinant on both sides, what we will end up with having is equal to det of lambda whole square is equal to 1. So this is exactly like what happens in any orthogonal group or any unitary group and everything. But in the case of Lorentz group, similar to orthogonal or unitary groups, but they are not exactly orthogonal or unitary groups. As I said, it is not SO4, it is SO31 because there is a disjunction between space and time, and it doesn't keep the length of the vector invariant, but something called the line element, which is x0 square minus or x0 square minus x bar square essentially, which is the reason why there is a difference essentially. But this property that det lambda square is equal to 1 will always be case. Instead of calling it as special or something, here we have a different name for Lorentz transformations. We call it as det lambda is equal to plus 1. In the case of orthogonal or special unitary groups, we call them as special. Here we call them as proper Lorentz transformations. Improper. Okay, proper Lorentz transformations or improper Lorentz transformations essentially. Okay, now there is also this is important actually. Then there is also a condition on orthochronous or okay, orthochronous or non-orthochronous transformations essentially. So where does that condition come from? That condition comes from something here essentially. Okay, let me. I'll then there is other condition. Now you take. Uh, we have again same the condition, same condition. Consider again. Uh, the same condition as above. So this is G mu nu lambda mu rho lambda nu sigma G rho sigma. But now consider the 0 0 elements essentially. Now consider the 0 0 component of the condition essentially. So I want to put consider the 0 0 component. So what we have the 0 0 component that is rho sigma is equal to 0 0. Now this is G mu nu lambda mu 0 lambda nu 0 is equal to Z 0 0. Okay. So this is nothing but G 0 0 is plus 1 essentially. This is nothing but is equal to 0 1. So this gives me the condition that lambda 0 0 square minus lambda I 0 square is equal to 1. This is coming from here essentially, just from here. So 0 0 0 0 take mu and 0 I 0 is equal to 1 because this is nothing. Okay, this is just coming from here. You take 0 mu is equal to 0 1 2, you have to some more mu is equal to 0 and I essentially. Okay, which means this implies lambda 0 0 I can either be greater than or equal to 1. Okay, if this is positive, essentially if this is positive, because this is always being positive. Okay, it's a square of it. So this can be either greater than equal to 1 or it can be less than or equal to minus 1 essentially. Less than or equal to minus 1. So these are the two conditions you'll get, because this is always positive definite, or this part is always positive definite. So since this is always positive definite, so lambda 0 0 square is also positive definite. So lambda 0 0 can either be 1 minus, if you take the this is the, because it has to be 1 minus some positive definite square whole square root. So from that you can get either it is greater than 1 or less than minus 1 essentially, less than minus 1. Now the condition that lambda 0 0 is greater than or equal to 1 is called orthogonous. And lambda 0 0 less than or equal to minus 1 implies non-orthogonous. So you can classify all Lorentz transformations as either proper, improper, and orthogonous or non-orthogonous. Okay, for example, essentially, so you can have as a P. So for example, the transformation P, which we will later on say it as parity, is improper and orthogonous. and T is improper and non-orthogonous. So any Lorentz transformation can be either proper or improper, or orthogonous and unorthogonous. Okay. So in fact, you can show that the set of, say for example, um, then you can worry about the products of these things and everything, but that is not important. Essentially what we are going to be saying, then there are other important thing, other things one can do, but what is important is that all proper transformations, orthogonous or non-orthogonous, form a group. Then all proper orthogonous transformations form a group. Proper and orthogonous transformations form a group. Proper, orthogonous, non-orthogonous, non-orthogonal. So you can think that each of them will form a group of their own essentially. Okay, let me write it down. Essentially proper, and then here we have orthogonous, then we have proper and orthogonous, okay, and then finally all together proper, orthogonous plus improper, orthogonous form a group. Okay, so this tells you that you can have subgroups of Lorentz group, subgroups of Lorentz group which form a group of their own essentially. That means there are some properties of essentially uh, 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 so why this is important, why we are trying to classify these things essentially. Okay, the point at the end of the day, what we want to know is, because we want to transform everything. Okay, so we said um, um, we said Lorentz transformations contain rotations, boost, parity, and parity means space inversion and time inversion. There are six, so total eight transformations: three boosts, three rotations, parity, time inversion, and everything. Now, whether they form a group of their own or not, what kind of group they form. So, first of all, discrete points we don't care. Essentially, P is improper and orthogonous, no problem. And T is improper and non-orthogonal. What about what about um, what about boost and rotation? Do they form a group of their own? The reason why we are worried about boost and rotation is boost and rotations always start with unity. So at the end of the day, what we want, if we want to have a infinitesimal transformation of Lorentz transformations, okay, they should always start with unity. This is because we wanted to connect it with this Lie groups. Essentially, Lie groups, I said, they should be start with unity and so they should be uh, there should be infinitesimal transformations around unity. They should be started with around unity. Now if you want to start around unity, they have to be, by the definition, okay, proper. Determinant should be positive. Essentially you can have, and lambda should always be, lambda 0 0 should always be positive essentially. So in principle what we need is, because we need everything should be greater than 1 essentially, lambda 0 0 should also be greater than 1. So what we need is that boost and rotations whether they form a group, yes. So they form a group. So they form a group themselves, boost and rotations essentially. So all proper transformations form a group. All orthogonous transformations also form a group, and proper and orthochronous transformations form a group. So this is important essentially. This will tell you that the group of just boost and rotations also forms a group essentially. The group of boost and rotations also form a group, are proper I think I did somewhere orthogonous. I think this should be orthochronous actually, orthochronous. Hi. In my excitement I must have mentioned orthogonous, but it's actually orthochronous. Orthochronous. I'm sorry. Okay. So what we have realized is that now the condition that on this particular condition essentially, this that the metric should always be invariant under Lorentz transformations, also puts subclassification also on possible, it also subclassifies uh, all possible Lorentz transformations essentially by choosing the determinant to be positive or negative. It is similar like what we have seen in what do you call in orthogonal groups or unitary groups essentially. So we always look for special unitary or special orthogonal groups, because in special unitary groups they always reduce the number of parameters essentially, and that they also set up that the determinant should always be positive, so that you can start with a unit matrix. Essentially the first matrix would always be unit matrix, and the unit matrix has a determinant which is positive. Because the unit matrix always has positive, we want proper orthochronous, because if you want to start with unity, okay, we want a unit matrix which is positive. Okay, like in special unitary or special or the orthogonal groups essentially. So in Lorentz transformations, instead of calling them as special, we call them as proper or improper. So we choose the positive determinant. So we are worried whether that the positive determinant would be, corresponding to boost and rotations essentially. And as we have seen essentially, then the first element lambda 0 0 also should be positive, because otherwise you end up okay. So for boost and everything, it's very important that it should be positive, because you want to always deform from unity. Okay, the first element of the diagonal element of the unit matrix should always be unity essentially. That is the reason lambda 0 0 should always be 1. Okay, so that is called orthochronous essentially. I don't know why today I said it as orthochronous. It's called orthochronous, and it cannot start with the negative terms essentially, because we want with a start with the delta mu nu essentially as a deformation of this thing. So we have seen that uh, that this these proper or orthochronous or non-orthochronous subgroups transformations of Lorentz group also form groups. Okay, okay, they also form continuous groups essentially. Like for example, all the proper transformations form a group, all the orthochronous transformations also form a group, and all the proper and orthochronous groups also form a group. And this is where our boost and rotations lie. This is where our boost and rotations lie essentially. Okay, but this is not true for all the other transformations of Lorentz group, because other Lorentz transformations of are parity and P and space inversion and time inversion. Essentially, as we have seen, the P transformations are improper and orthochronous, and T is improper and non-orthochronous. Essentially, this can be seen essentially because you are putting lambda 0 to be negative, okay, in T inversion, and it is improper because it doesn't start with unity. It doesn't start with unity. Both the things can be obviously seen. P has 1, it starts with 1 minus 1 minus 1 minus 1, so it is obviously improper. And whereas T is also improper because it starts with minus 1 and also non-orthochronous because lambda 0 0 is also negative, lambda 0 0. So P and T are obviously improper, and T is in particular also improper and non-orthochronous. Okay, whereas boosts and rotations, we need them to be proper and orthochronous because we want to start them as small deformations of unity, and with this we see that they also form a group of their own essentially as a subset. Just the transformations which are proper and orthochronous transformations also form a group of their own. So this becomes important essentially to start looking at building infinitesimal boost and rotations, and then looking at generators of the Lorentz group. Okay, I'll stop here, and in the next class we will look at the generators of infinitesimal Lorentz transformations, and that will pave way for representation theory essentially at some point essentially. Okay, in the next class essentially, in the coming sessions essentially, and then we will see the connection with spinors, and which is very nice to see essentially. Okay, I'll stop here, and thank you very much.